This is lesson 22.3 in your Springboard books. So today's goal, the student will interpret the parameters in a linear exponential function in terms of a context. So again, we're going to be interpreting exponential functions, just like we have for the last two lessons. So today, we are going to be graphing all of these exponential functions we've been talking about. We talked about exponential growth, we talked about exponential decay, we talked about the actual equation for an exponential function. So now we have to graph them. So here's where this is really important. You're taking a test on this and your calculator breaks. So I know that you are going to be able to do this with a calculator. You could plug this into the graph function and it would give it to you, and that's wonderful. But what happens if you don't have a calculator? And I will tell you that this happened to us last year. Desmos on the EOC, when you opened it during the test, it crashed the test. And so all of my kids had to take that test with no Desmos. You need to be able to do this without a calculator. Use the calculator to verify, not to do the work for you. So on page 333, we want to graph y equals 3 times 2 to the power of x. So we just need to know a few things, and it comes from our equation of an exponential function, which is f of x equals a times b to the power of x. And we just need to see what's in the place of each of these variables. So a in this case is 3, and b is 2. So we need to look at our initial value and our common ratio to determine how to draw this on our graph. What does initial value mean? Initial value means you haven't moved anywhere. It's the output when you started. So if we haven't moved in this equation, our output is 3. So if our input is 0, which means we haven't moved left or right, our output is 3. So we know we have a dot right here. And then we have this common ratio of 2. And what this means is our output is going to double every time we move one spot. So whenever I move my input one place, when my input is 1, my output is going to double from the previous output. So if my previous output was 3, what is my output going to be for 1? And if you don't trust that, you could do the math. We have y equals 3 times 2 to the power of 1 because we have an input of 1, or y equals 3 times 2 because 2 to the power of 1 is 2, or y equals 6. So again, our original output was 3. We're going to double it to 6 whenever we find the output for an input of 1. So now we want an input of 2. So if our input is 2, what happens? Well, our common ratio is 2, which means it's doubling every time. So if the previous output was 6, what is the output going to be when we have an input of 2? Well, it's going to double. So since it was 6, it's going to become 12, and we're actually off of our chart already. So if you don't trust it, do the math. We have y equals 3 times 2 to the power of 2. What's 2 squared? Well, that's 4. Y equals 3 times 4. 3 times 4 is 12. If you understand what each piece of the equation is telling you, you can graph it without doing any substantive math. I mean, you have to do a little bit of math. We have to know what double of 3 is and what double of 6 is. But we really didn't have to do this. We just had to trust that the math works. Then we need to connect these dots. And again, you should connect it better than I just did, but actually go through the dots. And this is what this exponential will look like. So let's try another one. So here we have negative 3 times 2 to the power of x. And we're still on page 333. And all we need to do is establish what is my a and what is my b. In this case, a is negative 3. B is 2. A is my initial value. That means when I haven't moved, or when my input is 0. If my input is 0, what is my output? So if my input is 0, my output is negative 3. So we have a spot right here. then for every input that I move by 1, I'm going to have a common ratio of 2, or it's going to double. So if I'm doubling my previous output, so when I had an output of -3 when my input was 0, when my input is 1, I'm going to double it. Double -3 is -6. And then when I move to 2, when I increase my output by 1, I'm going to double it again. So I need to go to -12. I could keep going, but I'm well off of my graph. So I'm not going to keep going. I'm just going to connect these dots and I get this. It is not linear. It looks a little bit linear, but it's because the graph is kind of condensed. It is not linear, it is curving. So this is an exponential function. All right, let's try this guy. We have 3 times 0.5 to the power of x. 3 times 0.5 to the power of x. So again, we have an a value and a b value. A is our initial value, it's where we started. B is what our common ratio is. So we started at 3, our common ratio is 0.5, or half. So we're going to start at 3. If I haven't moved, I'm at 3. So when my input is 0, my output is 3. If I haven't moved, my output is 3 because that's what my initial value is. Now, every time I move one spot in my inputs, I'm halving how big it is. It's going to half. So when I go to 1 as my input, my output is going to be half of 3, which is 1.5. And then when I go to my input of 2, it's going to be half of 1.5, which is 0.75. So it's a little closer to that. And then as I go to 3, it's going to half. Half of 0.75 is 37.5. So it's going to be kind of down here. And we're going to see that our exponential function does this. We're starting to get lots of cool pictures. And all of these pictures are going to tell us something, so we might want to pay attention to what's happening in each of these. So now let's try -2 times 0.5 to the power of x. And we have an a value of -2, a b value of 0.5, and we're going to do the same process. My initial value is -2, so that means when my input is 0, my output is -2. My common ratio is 0.5, or 1/2. So every time I move one spot, I'm going to half it. Half of -2 is -1. Half of -1 is 0.5. Half of 0.5 is 0.25, -0.25. And we are going to get, and I didn't mention, but in this one, and actually all of them, we never actually reached 0. I just drew it poorly. We're going to get really close to it. We're going to get really close to this axis, but we're never actually going to touch this axis. And there's a special math word, and it's my favorite math word. It's asymptote. An asymptote is this invisible line that your exponential function will never actually reach. Oftentimes it's 0. It is not always 0, but oftentimes it is. And I always get my kids to remember it because I tell them, do not touch my asymptote. That's right, not right. So asymptote is this invisible line that you're going to get really close to, super close to it, but you're never going to actually touch it. So don't touch the asymptote, guys. You will get arrested for that. So we are going to slowly approach that asymptote, but we'll never actually reach it because if we keep halving this, we'll get infinitely close to 0, but we'll never actually reach 0. So let's look at some of these graphs again. So we want to know, could I have looked at the equation and generally known what was going to happen? Not necessarily know exactly what was going to happen, but kind of generally know what was going to happen. And the answer to this is yes. If the a value is greater than 0, in this case 3, you can also look at part C. But if the a value is greater than 0, what happened? Well, we had a graph that went up. We had a graph that was getting larger value, that the values were getting larger. But what happened when the a value was less than 3? And if it was less than 3, all of our action, instead of happening in the positive quadrants, all of that action was happening in the negative quadrants. So if your a value is greater than 0, then you know that your action is going to be happening above the 0 value of y. It's going to be happening in the positive quadrants. If it's less than 0, like in this question, or in part D, I believe, yeah, or in part D, you'll see that all the action is going to happen in the lower quadrants. So positive a values happen above the y-axis, the x-axis. Negative a values happen below the x-axis. Then, what happens when the value is greater than 0, but b is less than 1? So if a is greater than 0, but b is less than 1, what was going on? We know that it's going to be in the upper quadrant because it's greater than 0. And that rule is never going to change. But b is less than 1, and what do we know that means? From last lesson, we know that that means this is exponential decay, right? So we know that this is going to be going on in above the x-axis somewhere, and we know it's going to start at 3 because we know it's 3 from right there. But it's going to decay because b is less than 1. And then we also know what happens when a is less than 0 and b is less than 1. So since a is less than 0, we know it's going to be happening below the x-axis. And since this is less than 1, since b is less than 1, we know it's also going to be decay. So we're going to see this thing slowly decaying or approaching that x-axis. Any decay approaches the x-axis. Those values are getting closer to x. So what can we do with this? So let's look at this question on page 336 to see what we can do with this. Alex believes that for the linear function f of x equals 50x and the exponential function g of x equals 2 to the power of x, the value of f of x is always greater than the value of g of x. Glenda believes that for a linear function f of x to always be greater than an exponential function g of x, the graph of f of x must be very steep while the graph of g of x must be very flat. She proposes graphing f of x equals 50x and g of x equals 1.1x to the power of x to test her conjecture. And our calculator is broken. And it crashes the test when I try and get on Desmos. And what in the world do I do? So we need to take this question apart. I need to know what's going on here. So first, we need to see, is Alex right? Alex is saying that f of x will always be greater than g of x. F of x is 50x and g of x is 2 to the power of x. And so one of the keys to doing this, generally these questions are true when you use small numbers, but as soon as you start throwing in big numbers, things don't work out so well for these problems. So instead of saying, like, let's test x is 5, why don't we test where x is like 100? So let's say this is 50 times 100, and this is 2 to the power of 100. And look, this is one of those exceptions where I say you can go use a calculator. Most people do not know what 2 to the power of 100 is off the top of their head. If you do, then you have more time than me, because I also do not know what it is off the top of my head, and I'm going to calculate it right now while I'm talking to you. All right, so here, when we do 50 times 100, we're going to get 5,000. You should not need a calculator for that. You can verify with a calculator for that, but you shouldn't need it. And here, 2 to the power of 100 is 1.26 times 10 to the power of 30. So it's actually way longer than that, but I just cut it off. In other words, this thing has 30 zeros behind it. it's way bigger than 5,000, which only has 3 zeros behind it. So we know that Alex is wrong. Alex cannot be right because we have given a single example of a number, the number 100, in which he fails. So Alex, sorry dude, you're wrong. So now Glinda believes that a linear function could always be greater than an exponential function if you make the linear function really steep and the exponential function really flat. So we're going to test and see if she's right. You will need a calculator for this one as well. And again, when we're looking at her f of x of 50x, which is the same as Alex's, but we look at her really steep exponential, or her really flat exponential function, it's tempting to try a small number and see if it works and say, well, like 5 is true, so this must be true. Avoid small numbers when you can test it with a big number. So let's try the same input. Let's try 100. So again, we're going to have 50 times 100, which is still 5,000, and you shouldn't need a calculator for that particular one. And then 1.1 to the power of 100. I would not expect my students to calculate that by hand, so I will allow a calculator on that one. And in this case, 1.1 to the power of 100, you get 13,780 and 612 thousandths. It's actually a little bit bigger than that, but it's infinitely bigger than that. And we have already proven that Glinda is also wrong. And here's the secret, guys. No matter how steep you make the linear function and how flat you make the exponential function, as long as it's growth, will always catch up to the linear function somewhere. It may not happen until you get to the number like 14,874,623, but it will eventually happen. So if you were ever given the choice on a test question between a linear and an exponential of which one will grow faster, or which one will give you the biggest number in the end, the answer is always exponential, as long as your b value is greater than 1. All right, your teacher should have some practice problems for you. Make sure that you practice this. Make sure that you use the different types of graphs and what you can learn from them to answer the questions in Springboard. If you have questions, ask your teacher. If you have questions, ask. We can't answer questions if we don't know that you need help. Thank you.